This is the lecture for lesson 3. This lesson is going to be all about radicals. In this first part, we are just going to talk about how we simplify radicals and use a few of the rules like product rule and quotient rule. So to get started, I know we previously talked about our perfect squares, and our perfect squares are able to be square rooted. Remember those perfect squares: 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, and there are more beyond that, but these are the ones you're probably the most familiar with. So if we just want to evaluate a square root, we can do the square root of 81. Well, the square root of 81 is 9. Now, a square root, you must do all the work underneath before you evaluate the square root. So we have to simplify underneath, like the next one says, the square root of 9 plus 16. We need to simplify what's underneath there. We cannot just square root both pieces. So we are going to add 9 and 16 together to get 25. And now if I take the square root of 25, I get 5. All right, so addition and subtraction underneath of a square root must be simplified before you do the square root. So that's a little note to keep track of. So addition and subtraction must be simplified before doing the root. So for this last one, the square root of 25 minus 16, well, that 25 minus 16 is all under the root, so I'm going to do that subtraction first. And at 9, so the square root of 9 then is 3. Unlike addition and subtraction, multiplication, if it is under a root, can be done separately. We can actually break the root into pieces as long as all of the pieces are being multiplied. Now, the other thing we're going to come across here, though, is not all of these are going to be perfect squares. So a few things we need to talk about here. So first are variables. So I can always square root an even power. So if I have, say, x to the 4th power, the way I do that is I just take how many times, because a square root is 2, how many times does 2 go into 4? And the answer is twice. So the square root of x to the 4th is x squared. Now, how do I know that? Well, I know that x squared times x squared gives me x to the 4th. And that's exactly what a square root is telling me, right? The square root of 9 is equal to 3 because 3 times 3 equals 9. You're looking for what times itself makes that number. If we have an odd exponent, we're going to have to use this rule here. So if we want to take the square root of y to the 5th power, what I'm going to do is I'm going to break it into the odd, even, and 1 left over. So I'm going to take one of them out, leave it here, and put the remainder in the other square root. The reason I do that is I know that I cannot do the square root of y. Any odd power, a single one, is not going to be square rooted. So that's going to stay where it is. But I can do the square root of y to the 4th, and that's y squared. The other way you can think about it is, again, it is a square root. So how many times does 2 go into 5? Well, 2 goes into 5 twice with 1 left over. So that's another way you can think about it. All right, so that's going to be kind of what we're going to do down here, and we'll work all the pieces together. So this first one has the square root of 128x cubed. 128 is not one of those perfect squares, so we're going to have to figure out how we break that down. And x cubed, well, that's an odd number, so we are going to have to, break that one down as well. So if I want to work with this, I want to work with my perfect squares. So the way I want to do this is I want to think, what perfect square can I break this into? Well, if I take 128 and I divide it by 2, I'm left with 64. So what I'm going to do is I'm going to rewrite this as the square root of 64 times 2, and then times x cubed. And if you want, you can put each piece separate. So the square root of 64, the square root of 2, the square root of x cubed. And we're going to do each piece as we can. I can do the square root of 64. The square root of 64 is 8. I cannot do the square root of 2, so that's going to be left over there. Now, the square root of x cubed, it's asking how many 2's are in 3. Well, there's 1 with 1 left over. So this, the square root of 128x cubed, simplifies to 8x square root 2x. So let's try again. So the square root of 24x squared y to the 5th. I'm going to do it slightly different here, just to show you the difference. So square root of 24, so let's see, I can break that into 2 and 12. No, that's not going to work. So I don't want to divide by, what, 4? Okay, let's do square root 4 times the square root of 6. That's going to give me the square root of 24. The square root of x squared. And then if you want, you can break your y's, put a single y, and then the remainders there. And you're going to work through which pieces you can do. So I can square root 4. I can square root the even powers. The square root of 4 is 2. The square root of x squared is x. And the square root of y to the 4th is y squared. And then anything that's not a perfect square is going to stay under the square root like that. All right, one more. So square root of 32, y to the 9th, x to the 9th, y to the 7th, z to the 10th. So let's see, 32, that's 2 times 16, so that'll work. So 2 times 16. Again, preference how you want to write it. X to the 9th, y to the 7th, z to the 10th. If you want to keep them all together, if you want to break them up, it's up to you what makes more sense to you. Okay, so looking at this, I can square root 16. The square root of 16 is 4. And I'm going to leave some space because I know I've got some variables here, x, y, and z. I cannot square root the 2. I have y to the 9th, or x to the 9th. I don't know why I keep saying y. X to the 9th. So x there. And so 2 goes into 9 4 times with 1 left over. Y to the 7th, odd. So I'm going to have a y left over. 2 goes into 7 3 times with 1 left over. And then we do the z. 2 goes into 10 5 times. So z is to the 5th power. Like multiplication, division can also be broken up across a square root. So if we have a single fraction under a square root, I can break it into the 2 individual pieces, and vice versa. If I have the 2 individual pieces, I can put it back under a single square root and simplify first. So let's go ahead and look at some examples. In this one, we have the square root of 8x to the 8th over square root of 2x. So because both pieces are under the square root, I'm going to rewrite them under one root so that I can simplify first. So if I have 8 divided by 2, that reduces to 4. And there are more x's on top. There are 8 on top, 1 on bottom. So in the end, there are 7 more on top. And what we want to do now is simplify the square root of 4x to the 7th, doing what we just did on the last slide. Well, I know I can square root 4. And I forget I don't have an eraser here. I can square root 4 and get 2. X to the 7th is an odd power. So I need to think to myself, okay, how many times does 2 go into 7? That's 3 times. And then there's 1 left over. So this entire fraction back here simplifies to 2x cubed times the square root of y. In B, they're already under one single square root. So the square root of 40x to the fifth over 8x squared. So again, I'm going to simplify what I can first. 40 is divisible by 8. That gives me 5. And x to the fifth over x squared, there's more x's on top by 3, because 5 is 3 bigger than 2. Can I square root 5? The answer is no. So the square root of 5 is going to stay where it is. Let's work with the x cubed. Can 2 go into 3? Yes, it goes in one time with 1 left over. So final answer for that one is x times the square root of 5x. Okay, last one is set up as the square root of 7 over 48. Now, looking at this, 7 over 48, that does not simplify. So for me, now I'm going to use the opposite rule and break it into its two individual pieces. I cannot do the square root of 7. 7 does not break down. It is a prime number, so I'm just going to have to keep it as it is. And then on the side, you take 48 and you say, okay, 48, if I divide by 2, 2 and 24, well, neither of those are perfect squares, so that doesn't work. 48 is 3 times 16. Oh, 16 is a prime number, or sorry, a perfect square. So let's use that. So square root of 48 is the same as the square root of 3 times the square root of 16. I'm going to simplify the square root of 16 as 4. I cannot do the square root of 3, so I'm going to leave it as the square root of 3 and the square root of 7 on top. Now, technically, this is not proper form, but I have not learned the rule yet for what to do with it. So we will show you a little later what we actually do here. So in math, you cannot leave a square root in the denominator. So again, this is technically not proper form, but for now, this is all we know to do. Now we're going to go on to adding and subtracting square roots, as well as rationalizing the denominator, which is the rule that we just said, hey, we're going to see in a little bit because we can't leave that square root in the denominator. Adding and subtracting square roots is just combining like terms. In order for two terms to be alike, they must have the same square root. So just like I can add 4x plus 4x and get 8x, I can add 3 root 2 plus 3 root 2 and get 6 root 2. So we're treating this as our term that we're trying to combine our like terms. So we may have to simplify to make them match first. Looking at the first one, we have 4 root 20 plus 3 root 5. In order for these to be like terms, they're both going to need to have the same square root. So 20, I know 20 is 4 times 5. So if I rewrite that as 4 times the square root of 4 times 5 plus 3 root 5. I can do the square root of 4 and get 2. Now, the 2 is joining this 4 out front here. So what I need to do is multiply those results together. So the 2 is going to join the 4, and we're going to have a root 5 left over and have 3 root 5 here. So that gives me 8 root 5 plus 3 root 5. And now the terms are matching. So 8 root 5 plus 3 root 5 is 11 root 5. Next one, 3 root 48 plus 2 root 27. We did 48 on the previous slide. So you're going to see some numbers that come back again and again, and you're going to get really familiar with knowing how to break those down. So 48 we broke into 16 times 3. And let's see, 2 root 27. So 27 is 3 times 9. All right, so what you're going to do is you're going to keep the number out front. I can square root 16 and get 4. So that 4 is going to join me outside with the 3. And that 3 I cannot square root, so it's going to stay underneath. I'm going to do the same with the next one. So the 2 is already outside. I cannot square root 3, so it's going to stay under the root. I can square root 9. The square root of 9 is 3, so it comes out front. So if we simplify what we have here, 4 times 3 is 12 root 3. 2 times 3 is 6 root 3s. And if I add 12 root 3s to 6 root 3s, that gives me 18 root 3s. We are going to do the exact same thing with our subtraction. We want to get our square roots to be the same so that we can now subtract the coefficients. So 32, I believe we saw 32 before, so 3 root 32x. So 32 was 16 times 2. I'm going to keep the x. Minus 2. Let's see, 18 is 9 times 2. So 9 times 2, and then there's an x. So let's simplify what we got here. So the 3 is outside. I can square root 16. That gives me 4. I cannot square root 2 or x. So 2x is going to stay underneath. Now we have a 2 out front. The square root of 9 is 3. So that's going to join my 2. I cannot square root 2 and x. So I now have 12 root 2x minus 6 root 2x for a total of 6 root 2x, because 12 minus 6 is 6. All right, last one. If you look, hey, they're already matching. So 7 root 18 minus 3 root 18. I can go ahead and simplify that right away. 7 minus 3 is 4 root 18s. However, based on our previous problem, we know 18 is not simplified. So I need to go the extra step and simplify that 18. So 18 was 9 times 2. The reason I picked those is because 9 is that perfect square. I can square root 9 and get 3, so it's going to join the 4 out front. I cannot square root 2, so it stays there for a final answer of 12 root 2. Next is rationalizing the denominator. So we've mentioned that keeping a square root in the denominator is not proper mathematical form. So what we're going to do is we're going to do the process called rationalizing the denominator. And what that means is we're just going to make the bottom denominator a perfect square. So whatever we need to multiply the bottom by, we're also going to multiply the top by. So let's take a look. I have the square root of 2 over the square root of 5. 5 is clearly not a perfect square. So what I can do is I can multiply the bottom by the square root of 5, and that would then give me the square root of 25. Why is that nice? Well, because I can square root 25. But in math, whatever you do to one part, you must do to the other part. So if I'm going to multiply the bottom by a square root of 5, I also need to multiply the top by a square root of 5. And according to our rules, if we have two individual roots multiplied together, I can combine them into a single root. So the square root of 2 times the square root of 5 is the square root of 10. The square root of 5 times the square root of 5 is the square root of 25. Again, why is that nice? Well, that's nice because the square root of 25 is 5, and the top stays the square root of 10. Now, please be cautious. What is inside of a root cannot simplify with what is outside of a root. So insides can work with insides, outsides can work with outsides. This is completely finished. There is nothing you can do because the 10 is under the root and the 5 is outside of the root. Okay, so let's take a look at the next one here. I've got the square root of 3x over 5y. None of these pieces can be square rooted. So again, I need the bottom to be a perfect square. Well, when it was just 5, I multiplied top and bottom by 5. Well, now it's 5y. So this time I'm going to multiply top and bottom by 5y. And let's see what happens. So on top, 3 times 5 is 15. There's an x and a y. And on bottom, 5 times 5 is 25. Y times y is y squared. We have made a perfect square in the denominator. I'm not going to touch my top. It is still a square root of 15xy. But on bottom, the square root of 25 is 5, and the square root of y squared is y, because 2 goes into 2 one time. This is the final answer. Next, we are going to see some higher power radicals as we go through the class, as we go through this lesson specifically. So we're going to look at one here. Now, when we had a square root and we had y squared like this, we asked how many times does 2 go into 2? Once. If I have a square root and I had x to the 7th, we know 2 goes into 7 3 times with 1 left over. We're going to follow that same process with a different root. So if I want to take, say, the third root of x to the 10th, you're asking how many times does 3 go into 10? Well, 3 goes into 10 3 times with 1 left over. So we're going to follow that same process. It's just that the third root now means that you need groups of 3 to make a perfect cube. I'm not working with a square, which is where you only need 2. I'm working with a perfect cube, which is where you need 3 of a kind. So looking here, I have the cube root of 2x over the cube root of y squared. So based on that, I need to have 3 total y's in order to be able to do this problem. So what I'm going to need to do is multiply top and bottom here by a y. Square root y. Not square root, cube root y. I apologize. Put the little 3 there. So I'm going to have the cube root of 2xy over the cube root of y cubed. We are not going to worry about the top. It's going to stay as it is, the cube root of 2xy. Now the bottom, I can simplify. How many times does 3 go into 3? And the answer is once. So y, or y to the first power, is now the denominator. If you look at every single one of these, the square root is no longer in the denominator, so these are proper form. Not all of them are going to look like what we just did. Here we see that our denominator is 2 root 5 plus 4. And we have a square root 5 in the denominator. Can't leave it there. So what we do here is we multiply by what's called the conjugate. And the conjugate means you're just going to change the sign that's between those two pieces on the bottom. So what I'm going to multiply top and bottom by is 2 root 5 minus 4. 2 root 5 minus 4. Okay, so on top, what I'm going to have to do is I'm going to have to do 6 times both of these pieces. It's being distributed in. So 6 times 2, 12 root 5, minus 6 times 4 is 24. Now, on bottom, I'm going to teach you the shortcut for now. This is what's going to be a difference of squares. So anytime you multiply the same numbers, 1 plus 1 minus, the result is going to be the first one times the first one minus the second times the second. So we are going to 2 times 2 is 4. Square root of 5 times square root of 5 is the square root of 25. Minus 4 times 4 is 16. So let's simplify what we can now. On top, it's still 12 root 5 minus 24. And the square root of 25 is 5. So this becomes 4 times 5, or 20, minus 16. So 20 minus 16 makes our denominator 4. And now what I need to do is I need to simplify this. Both of these pieces are being divided by 4. So I can rewrite this as 12 root 5 divided by 4 minus 24 divided by 4. And I can simplify those numbers. 12 divided by 4 is 3. Keep the root 5. 24 divided by 4 is 6. And there is your final answer. So this guy here has a square root of 6 minus the square root of 2 in the denominator. So I'm going to have to multiply by the conjugate, which is the square root of 6 plus the square root of 2 over the square root of 6 plus the square root of 2. What I'm going to do here is the bottom is the easier of the two. So I'm going to do the bottom first. The bottom is just because they're identical numbers with opposite signs, it's just first times lasts. It's a shortcut. So the square root of 36 minus the square root of 4. Now, on top, I cannot use a shortcut because they're all different numbers. So what I have to do is I have to FOIL them out. Okay, the reason I didn't have to FOIL this one out, if you don't believe me, let me show you. Square root of 6 minus square root of 2, square root of 6 plus square root of 2. If I FOIL this, root 6 times root 6 is root 36. Root 6 times 2 is plus root 12. Now I have negative root 2 times root 6, so that's negative root 12. Negative root 2 times positive root 2 is negative root 4. These middle ones cancel each other out. So that's why we can shortcut it with a conjugate. Now on top here, I'm going to have to FOIL this out. So 3 times root 6 is 3 root 6. 3 times root 2 is 3 root 2. Root 6 times root 6 is root 36. Root 6 times root 2 is root 12. So let's keep going here. I'm going to simplify the bottom. That's a little easier. The square root of 36 is 6. The square root of 4 is 2. And then let's keep working on the top here. So 3 root 6 plus 3 root 2. The square root of 36 is 6. And let's see, 12, we can break that into the square root of 4 and the square root of 3. So we're going to do some work here. Simplifying what we can on the top is just that last piece. The square root of 4 is 2. And then we have a square root of 3 there. And then on the bottom, 6 minus 2 is 4. And at this point, if they don't all reduce nicely, I'm not going to break them into individual pieces and reduce them. So that is going to be the final answer for this guy. The last part of this section is going to work with higher roots and then switching between what are called roots or radicals and rational exponents. So we first want to find the opposite of the third root of 27a to the 18th. So first off, that negative or the opposite is outside, so that's going to stay outside. Now, third roots are asking me what number times itself 3 times gives me this answer. And 27 is, in fact, a perfect cube. I can cube root 27, and I'm going to get 3. Because 3 times 3 times 3 is, in fact, 27. And then to do the variable part, how many times does 3 go into 18? That would be 6. So this answer is negative 3a to the 6th power. Next one, we've talked about odds and even roots. Anytime you have an odd power, you can do the negative here, and that negative is going to carry along. Now, I do not expect you to know what the 5th root of negative 3,125 is, but if you grab a calculator and type that in, you should get the value of -5. Last one here. Fourth root, there's a negative outside, so I'm going to carry the negative. The fourth root of 16, is there a number times itself 4 times that gives you 16? Yes, the answer is 2. 2 times 2 is 4, times 2 is 8, times 2 again is 16. How many times does 4 go into 24? The answer is 6. Okay, so we've talked a little bit about these positive and negatives working with odds and even powers. If I have, we know this, -64 to the 1/3 power is the same as the opposite of 64 to the 1/3 power. Is it going to be true for even powers? And the answer is no. Okay, you can do odds with a negative. You cannot do even powers with a negative here. And here's why. This means the third root of -64. This means the square root of -64. There is no way to take the same number times itself and get a negative. It doesn't work. If I tried two positives, 8 times 8 gives me 64. If I take two negatives, it gives me 64. In order to do a square root, your answer has to be exactly the same number and sign. There is no way to take two numbers with the same sign and get a negative. The rules of simplifying, multiplying, and dividing are all going to carry over to larger roots as well. So the first one, the third root of 8a to the 12th. Well, if I want to type in the third root of 8 in a calculator, that's going to give me 2. And then how many times does 3 go into 12? The answer is 4. You can always double check. 2a to the 4th times 2a to the 4th times 2a to the 4th. I should have 3 of them, and it should give me back to this answer. 2 times 2 times 2 is 8. a to the 4th, a to the 4th, a to the 4th makes a to the 12th. Okay, next one, the 4th root of 3 times the 4th root of 432. So I can multiply those two numbers together. 3 times 432 is 1,296. Now, I had to grab a calculator for this. I do not know what the 4th root of 1,296 is, so I grabbed my calculator and I got an answer of 6. Okay, last one, I have the 5th root of 32 over 1,024 x to the 15th. So because these are all under the square root, what I did first was I simplified 32 over 1,024 because 32 actually goes into 1,024 32 times. So 32 divided by 2 is 1. 24 divided by 32 is 32. And I'm going to carry my x to the 15th. What I'm going to do is I'm going to break my numerator and denominator separately so that I can do each piece on its own. Carrying the 5th root over. So the 5th root of 1 is 1. Any root of 1 is 1. The 5th root of 32 is 2. And how many times does 5 go into 15? The answer is 3. So 1 over 2 x to the 3rd power. Now we're going to see how these exponents and these radicals work together. So what we can have is we have a number to a fraction exponent. A fraction exponent means you're doing two things. You're raising to a power and then also taking a root. Now, it does not matter which part you do first. It is solely up to you. So what I'm going to do is I'm going to do two of them here, and I'm going to do each one differently. One of them I will do the root first, and the other one I will do the power first. So anytime you're using a exponent that is a fraction, so like here, 8 to the 2/3, the top number is your power, and the bottom number is your root. So this is saying I want to take the third root of 8 squared. So let's say for me, I want to do 8 squared first. Well, 8 squared is 64. So now I want to do the third root of 64. So I could grab a calculator, and I'm going to get the answer of 4. Now, let me show you, though, that I could have done the third root first. I would have written it maybe a little different. So I would have done the third root of 8, and then I would have put the squared outside. Well, the third root of 8 is 2, and 2 squared is 4. So it gives me the same answer. It's just a matter of which way your brain likes to do the problem. In a lot of cases, I like to go smaller and then go bigger after that, but it's up to you. So next one, 81 to the 3/4 means I want to take the fourth root of 81 to the third power. So for me, I like to do the fourth root of 81. I actually know that answer to be 3. And then I'm going to cube 3, which is 27. Final answer. We can also simplify fraction exponents using the same rules of exponents. So multiplying like bases, add the exponents. Dividing like bases, subtract the exponents. Powers to a power, distribute the power through. Things like that. So this one here, we have x to the 1/4 over x to the 3/5. So the way that I usually do them is I say, okay, where is the bigger number? Which is bigger, 1/4 or 3/5? Well, I can tell you that 3/5 is bigger. So then you have to figure out, well, how much bigger? So there's more x's in the bottom. We got to figure out how much more. So we're going to have to do some subtraction here. 3/5 is the bigger one, minus 1/4. Well, I cannot simplify this the way that it is because these are not like fractions. 3/5 does not combine with 1/4. I'm trying fifths and fourths. They're different terms. So we're going to get them to be a common denominator here. I can turn them both into 20s. Well, I do that by multiplying the first one by 4s. So 12 20ths is equivalent to 3/5. And I'm going to turn 1/4 into 20ths by multiplying by 5s. So 5 20ths. So 12 20ths minus 5 20ths, this is our label, is 7 20ths. They are like terms, so I can do the subtraction. So there is a 720 exponent on the x. Okay, next one, 3y to the 1/5 is raised to the 4th power all over y to the 3/10. So first off, I see I've got a 4th power that I got to take to both of these. 3 to the 4th power is 81. And when you raise a power to a power, you multiply the power. So 1/5 times 4 is 4/5. So then we're going to see we have y to the 4/5 over y to the 3/10. And we got to figure out which is bigger. Well, 4/5 is closer to the whole than 3/10. So there's more on top than there are on bottom. So we're going to take the larger power of 4/5 and subtract 3/10 from it. But right now they are different. This is fifths, this is tenths. So I need to make them the same. Well, 4/5 is 8/10. If I double both of them, 4 times 2 is 8, 5 times 2 is 10. Now they match. 8/10 minus 3/10 is 5/10. Well, that's actually easy. 5/10 is the same as 1/2. So 81y to the 1/2 power. A student did the following simplification. In which step, if any, was there an error made? What should be the correct answer if there was a mistake? So I'm going to give you a second. If you want to pause the video here, look through the problem, see if there is a mistake, and if there is, can you find it? Okay, so we have 9 times the quantity 4 minus 9 to the 1/2 power. So it looks like the student distributed 9 times 4 and 9 times 9 to the 1/2 power. Now the next line says 9 times 4 is 36, but 9 times 9 to the 1/2 is 9 to the 1/2 power. And this right here is your error. This is 9 to the first power times 9 to the 1/2 power. When you multiply like bases, you need to add their exponents. So if you have 1 and you add a half to that, that is 1 and 1/2. 1 and 1/2 is 3/2 as a fraction. So 1 and 1/2 is 3/2. So there's the error. If we fix this though, and let's see, they want us to find the actual correct answer. Let's see, 36 minus 9, square root of 9, and we want to cube that. So I'm going to square root first because the square root of 9 is 3. So 36 minus 3 to the third. 3 to the third is 27. So 36 minus 27 is going to give us an answer of